Hello, everybody, and welcome back to BioSC 140, Human Physiology. This video is going to cover S4P2, Part 2, Respiratory Physiology. So, gases move due to pressure differences, not concentration differences. And repeat that. Gases move due to pressure differences, not concentration differences. So Dalton's law is going to tell us about partial pressures. And we need to understand partial pressures in order to understand how gases move from the gaseous lumen of our lungs, the inside of our lungs, into the dissolved gas liquid medium of our bloodstream. So Dalton's law says that the total pressure is equal to the sum of the individual gases that make it up. So gas 1 plus gas 2 plus gas 3, total. It can also be written that the pressure of gas X, the partial pressure of gas X, is equal to the percent of the whole that gas is times the pressure. So gas movement is driven by partial pressure differences. You need to know Dalton's law in order to calculate these. So let's look at this box on the right. What direction is O2 going to move? Well, you're only getting part of the story right here. It says 20% up top, but 50% down below. This is a membrane where oxygen can pass through. Well, most students would say, oh, it's going to go from 50% towards 20%. And they would be correct if the pressures were equal. But let's look at this situation where the partial pressures of oxygen and the pressures of these chambers are different. The total pressure in the top chamber is 500. The total pressure in the bottom chamber is 100. So let's calculate partial pressure of oxygen. Well, total pressure is 500, so 500 right here. 20% oxygen, so 0.2 for 20% oxygen, gives us 100 as the partial pressure for oxygen in the top chamber. In the bottom chamber, we've got 100 for the total pressure, 50% or 0.5 for oxygen, so 0.5 times 100 gives us 50 as the partial pressure in the bottom chamber. This means that we have a higher partial pressure in the top than we do in the bottom. Things are going to go from the higher partial pressure to the lower partial pressure. Flow down. Gas movements is driven by partial pressure differences, and you need to know Dalton's law in order to calculate these differences. So let's practice. Let's practice Dalton's law. We live submerged at the bottom of an ocean of air. Evangelista Torricelli. So this guy, Torricelli, Tor, see the connection? A torr is a unit of pressure. So at sea level, atmospheric pressure is about 760 millimeters of mercury, or about 760 torr. Diablo Valley College is right about sea level. It's maybe 100 to 200 feet above sea level, but it's basically sea level. So let's calculate partial pressures. For nitrogen, nitrogen is 79% of the atmosphere. 0.79 times total pressure, 760, gives us a partial pressure of nitrogen of 600.4 millimeters of mercury at Diablo Valley College. Oxygen makes up 20.93% of the atmosphere. 0.2093 times the total pressure, 760, gives us a partial pressure of oxygen at Diablo Valley College of 159.07 millimeters of mercury, or torr. Carbon dioxide actually makes up a very small percentage of our atmosphere. I think most people think it's a lot higher, but it's about 0.4%. So the partial pressure for carbon dioxide in our atmosphere is 0.0004 times 760 gives us 0.3 millimeters of mercury for our partial pressure of CO2 at sea level or at DVC. How does that change if we start going up in altitude? So this mountain in the French Alps, Le Siran, I'm probably saying that wrong, Le Siran is 9,000 feet in elevation. To give you an idea of how tall that is, Mount Diablo is 3,800. So it's more than two Mount Diablos stacked on top of each other. The total pressure at the top of this mountain is 576. As we go up in altitude, total atmospheric pressure goes down. As we go up in altitude, total atmospheric pressure goes down. So let's calculate the partial pressures for these three gases at the top of this mountain. So we've got the percentage, so 0.79 for nitrogen times 570 for the total pressure gives us a partial pressure of nitrogen of 450.3. For oxygen, we've got 20.93%, so 0.2093 times 570, which is the total, gives us a partial pressure of oxygen of 119.5. For CO2, 0.0004 times 570 gives us a partial pressure of CO2 of 0.23 millimeters of mercury. So concentration stays the same. As we raise in altitude, concentration stays the same, but total pressure and partial pressure decrease. Let's look at this mountain in the Himalayas. This is Kardung La. It's a mountain in the Himalayas, 18,000 feet in elevation. That's really high. That's a really high elevation. Atmospheric pressure is 380 millimeters of mercury. 380 millimeters of mercury. So let's calculate it. For nitrogen, 0.79 times 380 gives us a nitrogen partial pressure of 300.2 millimeters of mercury. Partial pressure of oxygen, 0.2093 times 380 gives us 79.53 millimeters of mercury. Carbon dioxide, 0.0004 times 380, 0.15 millimeters of mercury is our partial pressure for CO2. Let's look at it at the top of Mount Everest. So 29,000 feet. 29,000 feet. Total pressure is 225 millimeters of mercury. So we've got 0.79 times 225 gives us 177.75 millimeters of mercury. Partial pressure nitrogen. 0.2093 times 225, partial pressure of oxygen of 47. 0.0004 times 225 gives us a partial pressure of 0.09 for carbon dioxide. So concentration stays the same as we gain altitude, but partial pressure goes down. Total pressure also goes down, but concentration stays the same. Right here we can see the partial pressure of O2 at different altitudes. A minimum PO2 to sustain life is 50 millimeters of mercury. Most people cannot reach the top of Mount Everest without the aid of supplemental oxygen. We need around 50 millimeters of mercury partial pressure in order to survive. So if you want to climb the top of Mount Everest, because of this partial pressure of 47 for oxygen, most people need supplemental oxygen. All right, so now that we understand how to calculate partial pressures, let's see how it relates to respiratory physiology. Henry's law says that partial pressures of liquids equilibrate to partial pressures of gases. So I told you that we're learning about, how oxygen goes from our alveoli, the lumen of our lungs, into our circulatory system well. Right here, we can see at the initial state, at time 0, we have 100 partial pressure of oxygen in the gaseous part and 0 partial pressure of oxygen in the liquid part. As we let time pass, we can see that oxygen molecules are being dissolved. They're moving into the liquid part of this chamber. And they're going to move into this liquid part of the chamber until the partial pressure in the liquid is equal to the partial pressure in the gaseous area. It's partial pressures that equate. It is not concentrations that equate. The concentration of oxygen in the gaseous part does not equal the concentration of oxygen in the liquid part. It's the partial pressure differences. Henry's law says the partial pressure of a liquid will equilibrate to that of the gas that surrounds it. Not concentration, it's partial pressure. So partial pressure is going to dictate how gases move from our lungs to our bloodstream and our bloodstream into our lungs. The final concentration in the liquid part depends on pressure gradient and solubility. So it depends on what's that partial pressure gradient and how soluble is something in the liquid medium. Oxygen has a very low solubility within water, so it's going to reach that 100 millimeters of mercury partial pressure with only a small number of molecules. CO2 is much more soluble, so it'll reach that 100 millimeters of mercury equilibrium point at a higher concentration. Carbon dioxide is about 20 times more soluble in water than O2. All right, so arteriolar partial pressure is dictated by alveolar partial pressure. Arteriolar partial pressure is dictated by alveolar partial pressure. So we talked about how at sea level, we calculated this actually, the partial pressure of O2 in the atmosphere is about 159 millimeters of mercury. We breathe in that atmospheric air and it mixes with some residual oxygen depleted air that we have in our lungs, and it drops down the partial pressure of oxygen to around 105 millimeters of mercury in our alveoli. That oxygen is exposed to blood that has a partial pressure of oxygen of only 40 millimeters of mercury. So this oxygen depleted blood that is flowing in via the pulmonary artery is exposed to the air in the alveoli. Partial pressure of oxygen is going to equate. So what direction is oxygen going to move? We have 40 millimeters of mercury pressure in our pulmonary capillaries. We have 105 in the alveoli. It's going to go from high partial pressure to low partial pressure. Oxygen is going to move into our bloodstream. By the time our blood flows out of the pulmonary capillaries, it's going to have a partial pressure of 105, just like in the alveoli. Henry's law, those pressures are going to equate. Those partial pressures are going to equate. With CO2, we have 45 millimeters of mercury partial pressure CO2 in our pulmonary artery. It's going to be exposed to the air in our alveoli. In the alveoli, we have 40 millimeters of mercury partial pressure CO2. Those two are going to equate. What direction is CO2 going to move? CO2 is going to go from high partial pressure in the bloodstream, in the pulmonary capillaries, to low partial pressure in the alveoli. That air in the alveoli, we're going to be respiring also. In the atmosphere, partial pressure of CO2 at sea level is 0.3 millimeters of mercury. We're going to breathe that air in. It's going to mix with the CO2 that's coming off and give us this lower number in the alveoli. And then as blood leaves the pulmonary capillaries, it's going to be at 40 millimeters of mercury. Henry's law, these levels equate. Let's see how it moves around our bodies. So we talked about how oxygen is going to, how when our blood leaves our pulmonary circulatory system, it's going to be at about 105 millimeters of mercury of oxygen, partial pressure. It's going to move into our arterial tree. There's going to be a little bit of venous blood mixed in, which is going to bring it down to about 100 millimeters of mercury, partial pressure oxygen. And where is the site of gas exchange? The site of gas exchange are the capillaries. So as our blood flows into our systemic capillaries, that 100 millimeters of partial pressure oxygen is going to be exposed to 40 millimeters of mercury partial pressure oxygen in our tissues. What direction is oxygen going to flow? Oxygen is going to flow into our tissues because 100 is higher than 40. It's going to flow from high pressure, 100, to low pressure, 40. High pressure systemic capillary, low pressure tissues. It's going to flow into the tissues. By the time blood leaves our systemic capillaries, it's going to be about 40 millimeters of mercury partial pressure, and it's going to flow back to our pulmonary capillaries to pick up more oxygen. Let's see how that story works with CO2. So we've talked about how CO2, or blood as it leaves the pulmonary capillary, is going to have a partial pressure of CO2 of about 40. It's going to flow through our circulatory system until it gets to our systemic capillaries. Our tissues are producing CO2. Our tissues have a CO2 partial pressure of 45. Systemic capillaries at the entrance have a partial pressure of 40. CO2 is going to move from high partial pressure to low partial pressure in our systemic capillaries. And by the time it exits our systemic capillaries, it's up at 45 millimeters of mercury partial pressure, and it flows back to our pulmonary capillaries, where the CO2 leaves the bloodstream and flows from high pressure to low pressure into our alveoli. If we're exercising, these numbers might be a little bit different. It'll be the same air that comes into our alveoli from the atmosphere. It'll be the same level of oxygen that's in our systemic capillaries. But when it gets to our tissues are using up oxygen at a higher rate. Our tissues during exercise, the partial pressure of O2 might get all the way down to 10 millimeters of mercury. So we're going to have flow of oxygen from the systemic capillaries into those tissues. When the blood leaves the systemic capillaries, that pressure, partial pressure O2, might be as low as 10 as it enters our venous tree. It flows back to our pulmonary capillaries, where this 10 partial pressure millimeters of mercury oxygen gets exposed to the 105 partial pressure O2 in our alveoli, and O2 moves from the alveoli into our bloodstream, bringing it back up to 105. Henry's law. All right. Let's look at some vocab. So apnea is normal breathing. Make flashcards, make vocab cards for these. Apnea, normal breathing. Hypernia is increased breathing to meet metabolic demands. Let's say you go running and you breathe hard because you're running. Hypernia. Hyperventilation is excessive breathing that's abnormal. So tachypnea, polypnea, other words for it, other words for the same thing. It's excessive breathing, breathing beyond metabolic demand. Hyperventilation is breathing beyond metabolic demand. Hypernia, breathing to meet metabolic demand. Let's look at carbon dioxide's journey with exercise. With carbon dioxide's journey with exercise, what changes? The thing that changes is you're producing more CO2 in your tissues because you're producing more energy. CO2 is going to move into your system. CO2 levels are going to be higher in your tissues. 50 millimeters of mercury, partial pressure CO2 in your tissues instead of 45 at rest. That CO2 is going to move into your systemic capillaries and travel back to your pulmonary capillaries, where it's going to move from high pressure of 50 in your capillaries to low pressure of 40 in your alveoli. How would this look at different altitudes? This will be a good practice if you printed out this page and tried it at the different altitudes. So right here at altitude, we have a lower atmospheric pressure. So we have a lower pressure of oxygen in our alveoli. Well, that just lowers this part. You know, pressures are going to equate. So we're going to have 40 PO2 moving, partial pressure O2 moving into our pulmonary capillaries. We're going to have it go from high to low, so 60 down to 40, but it's only going to equate. It's only going to be at 60 partial pressure of oxygen as it leaves the capillaries and goes around to the tissues. All right, and with that, I'm going to end this part of the video. If you have any questions, as always, please let me know. I'm here to help, and I will see you in the next video.